Chapter 6 is going to look at the standard normal distribution and some applications of the standard normal distribution. In Chapter 5, we looked at discrete probability distributions. Here we're going to talk about continuous probability distributions. So as a little bit of a reminder between discrete and continuous, we're going to look at this first example, example 1. It says, is it possible to have a shoe size that is equal to 8? Well, yes, it is. We know that lots of people have a shoe size of 8. The second part here says, is it possible to have a foot length of 8 inches? Depending on how accurately we are measuring, it could be possible to have a foot length of 8 inches, but it's never going to actually be 8 inches. So no. Our foot length is never going to be exactly 8 inches. We could take a microscope and we could zoom in, and we're going to find that our foot length is not exactly 8 inches. How many possible foot lengths are there? Well, depending on how close we zoom in, there could be an infinite number of foot lengths. And how can we graph the distribution? Before, when we looked at discrete topics, we had the ability to make a histogram. But here, if we made a histogram, because there are an infinite number of foot lengths, it's not going to work all that well. So the way that we graph it is we use what they call a density curve. We couldn't use a histogram because there would be an infinite number of skinny bars. So instead, we use a density curve, and we're going to talk all about what a density curve is. And then how do we find probabilities for continuous random variables? In the previous section, we counted up all the different ways that things could occur, and that was how we found the probabilities. But here, we're not dealing with discrete things anymore. Therefore, the way that we find this is we look at area under a curve. And we started to do this way back in chapter 2 when we talked about the empirical rule. We're going to expound upon that within this chapter. We're going to start off with some vocabulary and then apply this vocabulary. Our first word here is normal distribution. If a continuous random variable, it has to be continuous variable, has a distribution with a graph that is both symmetric and bell-shaped, and it can be described by this crazy equation. Now, we don't need to memorize the equation. We don't need to even know the equation. I'm just showing it to you so that you know that it talks about dealing with mean and standard deviation. So mean and standard deviation are going to be important here. A normal distribution has that bell-shaped curve. And in the middle of it is always going to be your mean. And the area is always equal to 1. or 100%. This is in contrast to a uniform distribution. A uniform distribution is a continuous random variable. So if we have a continuous random variable, again, it has a uniform distribution if its values are spread evenly over the range of possibilities. The graph of a uniform distribution results in a rectangular shape. We saw uniform as a shape when we looked at histograms back in chapter 2. So it'll look something like this. The area is still equal to 1. And two important properties. One, that the area is equal to 1. And the other one, there is a correspondence between area and probability. So some probabilities can be found by identifying the corresponding areas. So that's going to be a key thing, that area is equivalent to probability. And that's going to happen also with a normal distribution. Density curve. A density curve is a graph of a continuous probability distribution. And the requirements for a density curve are that the total area underneath the curve is equal to 1, just like with a uniform distribution. And every point on the curve must have a vertical height that is 0 or greater. So essentially, all this is saying is that it has to be above the x-axis. A density curve describes the overall pattern of a distribution, and the area underneath the curve and above any interval of values is the proportion of all of the observations that fall in that interval. Essentially, a normal distribution and a uniform distribution can be considered types of density curves. The uniform distribution, yes, it isn't a curve, it's a straight-sided figure, but we can still think of it as a curve. And there's a difference between the normal distribution and the standard normal distribution. Our standard normal distribution is going to be a normal probability distribution, except for it has some special characteristics. The mean is going to be 0, and the standard deviation is going to be 1. And that allows for the total area under its curve to be equal to 1. A standard normal distribution is going to still be bell-shaped. And since it's not easy to find areas of a bell shape, Table A2 in our textbook, or what they refer to as the standard normal probability table, is the way in which we are going to be able to find area underneath a density curve. Before we get into looking at normal distribution, we're going to look at uniform distribution. Example 2, it says the random variable x is uniformly distributed on an interval from 2 to 6. We want to find some probabilities. First, we're going to draw a picture to help us understand what's going on. It says we are on the interval from 2 to 6, and it is uniformly distributed. So essentially, we have a rectangle where our y-axis represents our probability of x, and our x-axis represents just our interval. If we think about this and we break it up here, there's 4 equal parts to it. The distance from 2 to 6 is 4. And the height then is going to be the probability of each of those happening, which is going to be a fourth or 0.25. Because remember, the area under the curve has to be equal to 1. Therefore, a fourth times a distance of 4 is going to be equivalent to 1. So here we want to know what's the probability that our x value is less than 3. Oh, anything that is less than 3 is going to be this piece here. So we can say that the probability that x is less than 3 is equal to a fourth. Or you could say the probability that x is less than 3 is equal to 0.25. We could also look at it from the graph. Here we have a width of 1 and a height of 0.25. 1 times 0.25 gives us area. Part B says, what if the probability that x is greater than 3? Again, we have our uniform distribution here with our probability of x. This is going to have a height of 0.25 because 0.25 times 4 gives us an area of 1. That whole thing has to have a total area of 1. And now we want greater than 3. So we're talking about these 3 1-unit pieces. Quarter unit pieces. So the probability that x is greater than 3 is going to be 3/4, or we could say 0.75. Again, we could use algebra to help us out. We could say that this distance along the horizontal axis is 3. The height is 0.25 or a fourth, and 3 times 1/4 gives us 3/4 or 0.75. Part C says to find the probability that our x value is between 2 and 4. Still on that same interval where we have a height of 0.25. And now we want between 2 and 4. We're talking about the first 2 bars of that. The probability that our x value is between 2 and 4 is going to be 1/2 or 0.5. We could take the approach of multiplying again to find that area. 2 on our horizontal axis times 1/4 or 0.25 gives us 1/2 or 0.5. And then for part D, what's the probability that x is equal to 3? Well, remember, we're talking about area here. We need a horizontal distance and a vertical distance. But if we're dealing with just a single number, like x is equal to 3, we don't have any width, right? We're just dealing with this concept of the line. So the probability that x is equal to 3 is going to be 0 because the width at 3 is 0. There is no width. So the probability that x is equal to an exact value will always be 0. Example 3, here we have the random variable x. It is uniformly distributed on the interval from 1 to 3. And we want to find the probabilities such that x is less than 1.5, x is greater than 1.5, x is between 1 and 2, or the probability that x is equal to 1. We would do the exact same thing as before. The only thing that is different this time is that our interval now is from 1 to 3 instead of being from 2 to 6. In example 3, we now have a horizontal distance of 2. So therefore, because our area under the curve has to be 1, our height is now going to change to 1/2. So for finding the probability that x is less than 1.5, we would find where 1.5 is, which happens to be a quarter of this whole area. Or we could just say that it's 1/2 on our horizontal and 1/2 on our vertical. 1/2 times 1/2 gives us a 1/4 or a quarter. The same thing kind of follows for part B, C, and D, just like we did in example number 2. Notice that I took all of the numbers in example 1 and divided them by 2. You should remember from geometry this creates similar figures, so we would expect all the ratios of the areas to remain the same.